Structural induction is the most general form of induction. In structural induction, we can have multiple object constants, multiple function constants, and we can even have function constants that have multiple arguments. Consider a language with two object constants a and b, and to start, a single binary function constant c. Here we see a list of some of the terms of the language. There's no graphical rendering in this case, as the structure is quite complicated. The structural induction rule for this language is shown here. If we know that phi holds of our base elements, and we know that whenever phi holds of any two elements, it holds of their combination, then we can conclude that phi holds of everything. In order to visualize a world where structural induction is appropriate, let's transport ourselves to a primitive chemistry laboratory. In the lab, we have two liquids, and we have enough equipment to combine the liquids in various ways. To combine the combinations with each other, and to combine those combinations with yet other combinations, and so forth. Back in logic land, our goal is to prove things about the acidity of the combinations we can create in the laboratory. Let's use the object constant 1 to represent one liquid. Let's use 2 to represent a second liquid. Let the binary function constant c represent the result of combining two liquids designated by its arguments. Finally, let's use the unary relation constant a to express the fact that a liquid is acid. Let's use n to express the fact that a liquid is neutral. And let's use b to express the fact that a liquid is a base. Now for our premises. We know that mixing two acids yields an acid. We know that mixing an acid and a neutral liquid yields an acid, and vice versa. We know that mixing two neutral liquids yields a neutral result. We know that mixing a base and a neutral liquid yields a base, and vice versa. And we know that mixing two bases yields a base. It's unclear what happens when we mix acids and bases because it depends on the concentrations, so we don't have a rule for that case. As a simple example of structural induction action, let's prove that if both of our liquids are acids, then every combination is an acid as well. In other words, given acid of 1 and acid of 2, we want to prove that for all x, acid of x. The proof in this case is trivial. We have our specified facts about A and B, and we have our general fact about the combination of two acids. These three items happen to match the premises of the structural induction rule precisely, and so we can derive our conclusion in one step. Okay, but now let's see what happens when one of our liquids is an acid and the other is a neutral liquid. Clearly, we can now have pure acids. We can also have combinations that are pure neutral, or we can have any mix of the two. The result is guaranteed to be either an acid or neutral, but that's all we can say. In other words, if we know that liquid 1 is an acid and liquid 2 is neutral, then the best we can do is to prove for all x, a of x or n of x. As with our last example, we can prove this result using structural induction. The proof in this case, however, is a lot messier. However, I think it's worth looking at it as it suggests the sort of complexity that's involved in doing inductive proofs with disjunctive conclusions, as in this case. There are 44 steps in this proof, but we'll skip over a lot of the details and just look at the basic structure of the proof. As usual, we start with our premises, the facts about the two liquids, as well as the general facts about our combinations of acids and neutrals. We could include all the facts about combinations, including the rules about bases, but since there are no bases, we can just omit those from the proof. As before, we deal with the base cases first. We use or introduction to disjoin our first two premises with other sentences so that the resulting disjunctions match the first two premises of structural induction for our desired disjunctive result. Here on line 7, we disjoin our premise that liquid 1 is an acid with the sentence n of 1. And on line 8, we disjoin a of 2 with our premise that liquid 2 is neutral. Now we prove the inductive case. To this end, we start a new proof and assume the inductive hypothesis. Our plan here is to generate our inductive conclusion from this assumption. The full details are in the notes. Suffice it to say that after 40 odd steps, we end up with the conclusion shown here. We know that the combination of x and y is either an acid or neutral under the assumption on line 9. We then can use implication introduction to generate the implication on line 42. And we can use two applications of universal introduction to generate the conclusion on line 43. Now we have everything we need. We can put all of the pieces together, two base cases on lines 7 and 8, and this inductive case on line 43, and we can apply structural induction to produce the desired overall conclusion. Although our proof here is messier than in the last case, the basic inductive structure is pretty much the same. Importantly, using structural induction, we can prove conclusions that would not be possible otherwise. It's induction in any of these forms, linear, tree, structural, is an extremely powerful proof method, and one that we should all master even when it gets messy.